Hello and welcome back to Organic Chemistry Semester 1. For the next chapter, we're skipping a little bit ahead in your book. Last chapter was chapter 6. Now we're moving into chapter 10. Last chapter, we focused on certain mechanism patterns. And this chapter, we're going to add just a little bit to that. So we're going to do about the first half of chapter 10. I believe it's sections 1 through 7. We'll make sure to cover that in each lecture video description. If you look down below, I'll make sure to tell you which sections are going to be covered. And then the last half we'll save for next semester. So just keep that in mind. But it's really important that we talk about radicals now because radicals represent another type of mechanism that occurs pretty frequently in organic chemistry. So if we don't have a good understanding of radicals, then we're not going to really be able to understand a lot of the reactions moving forward. So we kind of want to lay down the groundwork here, talk about a few general characteristics of radical reactions, and then get into a few specific reactions as well. Okay, so remember, this word radical represents basically just a single electron in a place where a lone pair normally would be. So like you have basically an unpaired electron. That's what gives you this idea of a radical or a free radical. These are the result usually of what's called homolytic bond cleavage. If you recall from the previous chapter, we talked about bond dissociation energies and determining the thermodynamics of a reaction from bond dissociation energies. Those bond dissociation energies are based on this homolytic bond cleavage like so. Now, when a bond cleaves homolytically, basically one electron from the sigma bond here that contains two electrons, so one of these two covalent electrons is going to go with each atom. So when we want to represent that, rather than showing a pair of electrons is moving, instead what we're going to do is we're going to have what's called a half arrow or a fishhook arrow, which looks like this. So what this diagram is saying right here is it's saying, okay, this pair of covalent electrons, it's going to split up. One of them is going to go to the X side. So you just draw like a little fishhook sort of arrow or a half arrow. And then one of them is going to go to the Y side. So that also gets a fishhook arrow there. And that produces basically X and Y, but X and Y with a single electron that we're going to just represent with a little dot. And you can represent it however you like, but you know, like a lone pair is two dots, right? So that you know that the dot is the electron form. So we're just going to kind of follow along the electrons in that way. Right, and so this is the key distinction when we're looking at radical mechanisms. We need to make sure that we understand the single barbed arrow is like a half arrow. It follows the movement of a single electron. Whereas what we've seen so far, the double barbed arrow, that's when you show the motion of two electrons. Right, so the example would be like in loss of a leaving group. When you follow the pattern for loss of a leaving group, that's going to use the double barbed arrow where one covalent bond is going to go entirely to one atom, and it's going to form a lone pair on that atom as it leaves the rest of the molecule. Whereas here, this is homolytic, so we're going to use the fishhook arrows here. Okay, so radicals, of course, have their own structures that we need to keep in mind. So just briefly, it's an important kind of time to review carbocations and carbanion structures as well. So carbocations occupy empty p orbitals, and the carbons that have these empty p orbitals are sp2 hybridized. They're trigonal planar. Whereas carbanions are going to be in a filled orbital, generally an sp3 orbital, just generally speaking. And so these are sp3 hybridized, and so they fill this hybrid orbital here. So just keep in mind that it's a little bit different. Now, radicals can do either of these depending on the scenario they find themselves in, basically the position they're in. As we're about to find out, some radicals have resonance, and in order for them to be in resonance, you know, forming a new pi bond, you have to have pi overlap. So radicals that have pi overlap with a neighboring pi bond, so like let's say they're in an allylic or a benzylic position, those radicals are going to be in unhybridized p orbitals. Now that's not all the time, and so a lot of times we'll see sp3 hybridized radicals. These sp3 hybridized radicals, of course, just like it says, there's only sp3 orbitals available, so the lone electron has to be residing in the sp3 orbital. Now this sp3 orbital is going to be Just think about it here. Basically, like when you go from a carbanion has 2 electrons in its sp3 orbital. The radical only has 1 electron in its sp3 orbital. It's gonna push a lot less on the other bonds. So rather than getting a normal tetrahedral structure like you would expect from an sp3 hybridized structure, so this would be like a trigonal pyramidal molecular geometry, it ends up being very shallow because there's just not as much electron density pushing on these 3 here. So you get this shallow pyramid and it can invert freely. Okay, so radicals are neutral. There's no formal charge associated with them. But because they lack an octet, if you have a radical, that means you are missing an octet. That means they're missing electron density. So we call them electron deficient. And so because they're electron deficient, they actually follow the same stability trend as carbocations. So following along here, if you recall from carbocations, methyl radical in this case is the least stable. A primary radical, that's 1 carbon that's bonded to 1 other carbon. That's more stable. Then secondary, that's where your radical carbon is bonded to 2 other carbons. And then finally, tertiary carbons are the most stable of this group, not taking into account resonance effects, because it's bonded to 3 different electron donating carbon groups here. Now, keep in mind that bond strength is something that's going to be inversely proportional to the carbon radical stability. Basically, the more stable your radical is, you can imagine the more stable the products are going to be. So the stronger that bond is going to be. So as you go from a methyl to a primary to a secondary to a tertiary carbon hydrogen bond, you're decreasing the bond dissociation energy that's required. And so it's just easier to basically abstract radical hydrogen in one of the patterns that we're about to see in this lecture from a tertiary carbon than it is from a methyl or a primary carbon. And you can see it goes down pretty regularly from 435 kilojoules per mole to 410 for a primary to 397 for the secondary and 381 for the tertiary. So just keep in mind, like the more stable the resulting radical is going to be, the weaker the bond is and the easier it is to remove it. So that shows up in the bond dissociation energies. Okay, so I already mentioned this, but just like carbocations, radicals have a certain type of resonance. It's basically resonance delocalization that you can form. And the good news is the positions, just like carbocations, are going to be in the same places. So the same places you look for resonance for carbocations, you're going to look in the same place for this radical. Now, the mechanism looks a little bit different when we actually draw it out. So here, this is an allylic position, right? We have our pi bond here. So these are the vinyl positions here. So the neighboring atom is an allylic position. So this radical is in resonance with basically this radical can be on carbon 1 or on carbon 3 as we look at it left to right. So looking at it here, the way that this works is basically the radical electron is going to form a new pi bond between, as we look left to right, carbons 1 and 2. At the same time, so simultaneously, the pi bond between carbons 2 and 3 are going to split up homolytically, where basically one of these is going to go to the far carbon here. 1 electron is going to fishhook, and you're going to see it goes to the far carbon. And then the other one swings over and forms the new pi bond between carbons 1 and 2. So very similar to like with a carbocation, if this were a carbocation, we would just swing both of these pi electrons over. Now it's a little more complicated. We still have that pi overlap to consider, but now we are taking 1 electron from the pi bond, our radical electron, we form our new pi bond, and then the other electron from the pi bond gets left over as a radical on the far carbon. So it's a new allylic carbocation. Or I'm sorry, a new allylic radical. I said that wrong. Okay, now there's the allylic position, then there's the even more stable benzylic position. And the reason that there's more stability in a benzylic position is because there's more resonance. And I hope that's something that you've learned throughout the semester already. basically the more resonance structures you have that can represent a certain molecule, the more stable it's going to be. And so you can follow around this radical here all the way around from the benzylic position, then to carbon 2, then to carbon 4, then to carbon 5, and then back onto the benzylic position. So more resonance structures move the electrons around more, so it's more stable. So what that means is with the addition of those resonance structures, now we have these new positions for radicals that basically mean that an allylic radical and a benzylic radical are going to be more stable even than tertiary radicals. So it's not correct to say that, okay, here, this is an allylic position. So you might think, oh, this is like a primary carbon. But that's not the case because this carbon's actually in an allylic position. So its radical is even more stable than the tertiary. Same thing with this benzylic position. And because of that stabilization, the bonds become even easier to break. 364 kilojoules per mole for the allylic position, 356 kilojoules per mole for the baseline benzylic position. Now, on the other hand, if you have a vinylic or an arylic radical, those are extra unstable, basically. What happens there is this vinylic radical, in order for us to break this carbon-hydrogen bond, if you notice, like all the bonds that we've broken so far are carbon-hydrogen sp3, sp3 to 1s hydrogen bonds. And here, that's not the case, right? This is an sp2 hybridized carbon. So this particular bond here is the result of like a sigma overlap between an sp2 orbital and a 1s orbital of the hydrogen. So the hydrogen doesn't change, but the carbon being sp2 does change. The more s character you have in your bonding, in your atomic orbital, the lower in energy it is, the harder it is to remove the electrons from there. So the electrons are really stable in that sp2 orbital. They have a lot of s character. They're closer to the nucleus. So it's harder and harder to break these vinylic or arylic positions. So you just don't see that very much, a vinylic or an arylic radical. Okay, so we're going to talk about a few different patterns here. We've got, so it says 6 at the bottom of the slide, but really it's more like 3. There's just forward and reverse of 3 different mechanisms that we want to learn. So we mentioned all of these similarities to carbocations so far, but in reactions, the radicals are going to behave a lot differently. The first thing is there's no rearrangement of a radical. So like here, you see this carbocation, you should immediately think, oh, there's going to be a 1,2 methide shift, so we can form the tertiary carbocation. That's not going to be the case with a radical. It's not going to rearrange in any ways. So that can be a good news, but we just have to keep that in mind that we're following different rules here for the radicals. And here are the mechanisms that we're going to be using, the arrow pushing patterns, excuse me, that will be used in the mechanisms that we talk about with radical chemistry. So starting off with homolytic cleavage. We already talked about this, but it's just basically where you have a sigma bond, one electron goes on either side and it splits the bond. And again, the electrons are distributed equally. So each X gets an electron from here. Next up, we have what's called addition to a pi bond. So this one looks a little different. This is going to be our first new looking pattern here that we've seen. But this addition to a pi bond, basically it takes the radical X here, so the radical electron from X in this case, and we're going to form a new bond a new sigma bond by taking that electron along with one of the electrons from the pi bond. So this forms a new bond here. That's why you don't see anything here. It doesn't look like anything's happening, but these two electrons are forming a new bond together. So that's kind of where we're pointing, is between the carbon and the X. So that's saying, oh, that's our new bond. Then we have here the radical. So the other electron left over from the pi bond is going to go to the carbon here, and that forms that's basically the new radical in this case. So after that, we have what's called hydrogen abstraction. Importantly, this is not the same thing as proton transfer. Proton transfer, you have your base donating a lone pair to a proton. The proton's bond to its previous compound is broken, to the acid is broken. That's not the case here. We have a radical starting, basically, and we're forming a new bond from that radical to a hydrogen atom. And the way that happens is it takes one electron from the hydrogen, in this case, R bond, whichever one it happens to be. And that leaves you with an R radical along with the XH bond, whichever radical X was. In the same way, you can have halogen abstraction. It's the same thing. The only difference is you have a halogen rather than a hydrogen that's being transferred. So here we have a radical R that's forming a new bond from R to X. We take the single electron from R and we take one of the electrons from the XX bond. That forms our new RX bond. That's what we get over here. What's left over is the remaining electron in the XX covalent bond is left behind with the other X, leaving us again with a radical. Okay, now the reverse of addition that we had covered on the last slide is what's called elimination. So this is where your carbon X bond can break, and it breaks homolytically, where you have the X getting one electron, and then the other electron in this carbon X bond is going to reform the pi bond that we had from the addition, if you recall. So like going back to the addition, that's here. This is just the reverse of that mechanism, where now all of a sudden we're reforming our pi bond. We're taking this electron, taking one of these electrons here, and then one electron is leaving with the halogen or the X. And then finally, there's coupling. Coupling is like a termination step. It's going to end the cycle of producing radicals here. And this is just where two radicals meet up and they're like, hey, you've got a lone electron, I've got a lone electron, why don't we share? So they form a covalent bond from two radicals. Now I mentioned that these are basically three patterns that are kind of split up. And sure enough, it's just exactly like that. There's really three processes, and it's either forward or reverse. So homolytic cleavage is where you go from the sigma bond to the two radicals. Coupling then takes those two radicals and reforms the sigma bond. You can take a radical and a pi bond. You do get the addition to a pi bond that gets you this radical here. But then you can also do the elimination. The elimination process just takes you back to the pi bond with a radical. And then finally, you have hydrogen or halogen abstraction. And basically what this is it's its own kind of forward and backward pattern. Like here, the X abstracts the hydrogen from R, giving you the R radical and XH bond. But you can imagine the reverse process where R radical extracts the hydrogen from X and gives you the X radical with the HR bond. So yeah, that's really the three processes that you have to worry about. So I know these mechanisms look kind of scary when you see all the different arrows, but remember we have to write in more arrows because we're following individual electrons around rather than pairs of electrons. Okay, so next up, I know I mentioned one of these already, but these steps can be, in a radical mechanism, we're gonna have like three different phases. You've got the initiation phase, the termination phase, and the propagation phase. And this is all about like how you generate a radical, and then once you have a radical, does it keep making more radicals or does it end? So like initiation is going to be where you're going to take a non-radical species like a halogen, like this could be chlorine or bromine, for example, and you split them up and you make two radicals. So there now we have our radicals, we can do our radical chemistry. Propagation, that's the middle phase. That's where you're taking a radical, it reacts with a non-radical, and it forms a new radical. So it's like you start with the radical, you end with a radical. That's what we saw when we had the addition to a pi bond. We started with a radical, we had a different radical. A hydrogen abstraction or halogen abstraction, same deal. You start with a certain radical, you end with a different radical. And then finally, elimination is another example where we had this pi radical here, and we reformed our pi bond and the X radical here. And then finally, termination is exactly what it sounds like. That's where you take two radical species, they form a non-radical species. And generally speaking, this is going to happen when you have a coupling reaction. It's the only way to kind of like even out the number of electrons, right? You got to be able to take those electrons from somewhere. And so the two radicals hit up, they couple. Now you no longer have an electron. I'm sorry, you no longer have a radical. Okay, so yeah, we're going to talk a lot about those when we have the different mechanisms. We're going to go specifically talking about initiation, propagation, and termination stages. We need to be able to identify those by the end of the chapter, but for now, it's good enough that we are practicing with those words. Okay, and that does it for this lecture. There's more practice in the lecture activity down below. I will talk to you guys soon. Okay, thank you.